Thank you everyone for attending my presentation today. My name is Nathan Henderson. I am a doctoral student at North Carolina State University, and I am presenting my paper titled Enhancing Student Competency Models for Game-Based Learning with a Hybrid Stealth Assessment Framework. This work is supported by North Carolina State University and Concord Consortium. Recent years have seen a growing interest in game-based learning environments within the educational domain. These digital games help promote engagement in students throughout their learning experience, which enhances learning outcomes and accommodates mastery learning. Additionally, these game-based frameworks can support individualized sequences of challenges and just-in-time support, which addresses generalizability issues with a one-size-fits-all approach. Finally, digital games support the dynamic analysis and prediction of student competencies through the development of data-driven modeling approaches using data captured from these environments. One approach to student competency modeling in game-based learning is stealth assessment. Stealth assessment builds on evidence-centered design and is able to robustly assess student learning through data-driven modeling implemented using non-intrusive, behind-the-scenes methods based on students' activities in game-based learning. Such assessment models can help inform effective pedagogical strategies, including adaptive challenge selection and scaffolding within game-based narratives. In this work, we investigate an alternative stealth assessment framework using a game-based learning environment for teaching genetics. We employ an ensemble of stealth assessment models trained to predict 15 distinct student competencies utilizing static and sequential modeling within single-task and multitask frameworks, and we demonstrate how our hybrid stealth assessment framework is an effective implementation of heterogeneous modeling approaches. First, I would like to provide a brief overview of prior work within student modeling as well as stealth assessment. There has been a variety of machine learning-based approaches to student modeling. Some approaches include supervised learning techniques such as Bayesian networks and gradient boosting, used for student performance and learning prediction. Reinforcement learning has been utilized in game-based learning environments for multi-objective and deep learning contexts. In this work, we evaluate different methods of multitask learning for our student modeling, a method that has been explored within student modeling for MOOCs as well as item-level student performance within game-based learning environments. A number of computational methods have been used within evidence-centered design-based stealth assessment, such as Bayesian networks, hidden Markov models, and long short-term memory networks, or LSTMs. However, this work typically implements a homogeneous modeling technique for each of the stealth assessment target variables, an approach that we seek to improve upon in the study. Next, I will provide a brief overview of our dataset used in this work. Jenny Venture is a digital game that teaches middle and high school students various genetics topics. This game consists of 60 distinct challenges that are divided into 6 levels of increasing difficulty. Each level consists of different missions that are comprised of the challenges. Should a student need assistance during a particular challenge, 3 progressively directed hints can be displayed to students. Students can attempt any challenge in any order and can also quit a challenge at any time. The first figure is the layout of the game within a certain challenge, and the second figure demonstrates how the challenges within a single level are divided into certain missions. The design of the game is guided by the next generation science standards and explores genetics by the breeding and studying of drakes, which are a model species of dragons. Our dataset is comprised of pretest survey, gameplay interaction trace data, and post-test survey data from 316 students, which was collected over the course of several days. The post-test survey was comprised of 28 questions corresponding to 16 distinct genetics concepts. The first figure is a histogram showing the distribution of the number of challenges completed by the students, with most students completing around 80 challenges, with a range of 5 to 248 challenges each. Next, I will describe the methodology of our work. Evidence-centered design, or ECD, is the foundation of our stealth assessment framework. It is a systematic approach to designing and developing reliable knowledge assessments which can provide support for adaptive scaffolding within digital games, as well as additional insight into student performance and learning trajectories. ECD is comprised of 3 distinct models: the task model, which is the challenges within our game, the evidence model, which is the low-level student actions which inform our stealth assessment framework, and the competency model, which is the 16 genetics concepts, which is informed through expert review of classroom learning goals and state science standards. The ground truth for each student's competencies are acquired from their individual post-test scores. Because gameplay actions can vary depending on the challenge, we engineered 10 generic representations that represent a student's gameplay independently of the challenges played. This includes their pretest survey score, challenge information, movements, and hint usage. These representations will form the basis for our static and sequential feature vectors we describe in the following slides. We evaluate a variety of single-task and multitask static models, which are trained on student-level gameplay features, so 316 individual feature vectors. Our single-task models delegate a single model for each of the competency scores for each student, while the multitask approach involved a single model used to predict all student competencies at once. Features were based on time spent during gameplay, challenge success rate, movement accuracy, hint usage, and levels played. Static models included elastic net, gradient boosted regression, and random forest. Note that gradient boosting regression does not support multitask learning. We take a similar approach of evaluation of both single and multitask models with our sequential competency models. Summative features on a challenge level were engineered for these models based on averages of time, movement, hint usage, and challenge success across a student's individual gameplay trajectory. These 8 features were combined with the previous 10 challenge-level generic feature representations to have a total of 18 sequential feature vectors to train our respective models. 3 variations of LSTMs were used alongside gated recurrent units for both single and multitask models. In addition to standard LSTMs, we evaluate bidirectional LSTMs as well as LSTMs that implement a self-attention mechanism. Bidirectional LSTMs are a variation of LSTM that contain 2 input layers on opposing sides of the hidden layer, allowing the model to retain temporal information based on the past and the future of the input sequence, as opposed to only the past. A self-attention LSTM provides additional temporal context beyond contiguous feature vectors by utilizing a weighted sum of hidden representations of the entire sequence. The static dataset consisted of 316 feature vectors, 1 per student. The sequential dataset consisted of about 29,000 subsequences after subsampling using a sequence length of 10. We used 27 of the post-test survey questions to calculate 15 distinct student competencies, removing 1 competency that contained 0 variance and was predicted perfectly by all models. Each competency score was the number of correct answers for post-test questions related to a single competency over the total number of post-test questions for that competency, resulting in a concept having a corresponding competency score between 0 and 1 for each student. The data was split into 80% training and 20% held-out test data, with the optimal model being chosen using 5-fold cross-validation. The datasets were split along a student level to avoid data leakage from the same student within our model evaluation, leading to artificially inflated results. Hyperparameter tuning was performed during cross-validation using an iterative grid search, so please refer to our paper for additional details on the final hyperparameter tuning results for each model. The justification behind our hybrid stealth assessment framework is the ability of the framework to adapt to trends that exist or don't exist across one or multiple concepts within our ECD model. Student competencies can vary widely with regards to each concept's correlation to specific questions and post-test scoring methods, as well as each concept's correlation to specific gameplay features or levels. By implementing both static and sequential variations of single-task and multitask models, the long-term and short-term tendencies within each student's gameplay is explored on a challenge and a student level. This includes modeling independently and correlated concepts, as well as capturing temporal trends that may exist within certain student-level data. Our use of both single-task and multitask models ensure that the hybrid framework is able to adequately capture interwoven trends within the data corresponding to multiple concepts, while the use of static and sequential features allows the hybrid framework to recognize temporal trends within a single student's gameplay trajectory at a challenge level. This provides a unique advantage compared to other homogeneous stealth assessment approaches that utilize a single model for all ECD concepts. Here is a chart reviewing the models used for each static, sequential, single task, and multitask approach. As this diagram shows, we seek to take the optimal model for each competency and combine them into a single hybrid framework that utilizes the predictive capacities of different model types for the different concept-to-question mappings and potential temporal trends in the student gameplay trajectories. So next I will review the results of our work. The results of our regression models are presented in terms of R-squared. The GRU performed relatively poorly with an average R-squared of 0.102 across single-task and multitask models, while the highest performing model was the static random forest. Random forest may also perform relatively well as a competence model because it uses an ensemble approach, making it more robust against overfitting. The single-task bidirectional long short-term memory network performed the highest for two concepts, as well as the multitask elastic net. The single-task LSTM and the multitask random forest, bidirectional LSTM, and self-attention LSTM were optimal models for one concept each. The gradient-boosted regression, single-task GRU, and single-task self-attention LSTM performed relatively poorly and were not the highest performing competency model for any of the concepts. The multitask models were the most effective approach for 5 of the 15 concepts, while the single-task models were the most effective for the other 10 concepts. The performance of each of the models varied depending on the concept number for the most part. In other words, the concepts that had a high R-squared score for one model also had a high R-squared score for most of the other models. This could be because how well a gameplay feature predicts a concept can depend on the type of concept. In other words, some concepts are harder to model irrespective of the modeling approach used. The optimal models for each competency distributed across both static, sequential, single, and multitask models within the hybrid stealth assessment framework achieved an R-squared value of 0.241. This outperforms a framework that only used the most frequently occurring single model, the static random forest. If we use a homogeneous approach with this model, the performance of this network is 0.206. Therefore, our hybrid framework achieves a 17% increase over this single model approach. Our observation that the use of multiple models in the hybrid stealth assessment framework would induce higher performance than using a single model can be explained by the fact that static, sequential, single task, and multitask models were all selected as an optimal model at least once. Single task models produce the highest performance on competencies corresponding to a single post-test question, which is expected behavior due to the absence of interrelated conceptual trends. Surprisingly, single-task models were also the highest performing model type on concepts mapped to multiple post-test questions, a possible indicator that interwoven conceptual relationships may not be prevalent in this particular context. However, the model's performance on singularly mapped concepts was relatively low. We further analyzed the framework's performance relative to the conceptual overlap between questions. A concept is considered a multiple question concept if it shares a correlated question with one or more separate concepts. As indicated here, the student performance on multi-question concepts was significantly higher than single-question concepts, a trend that is reflected in the performance of our stealth assessment framework as well. However, the optimal models for the multiple question concepts were primarily single-task models, indicating that multitask modeling across all concepts is actually detrimental in terms of achieving higher predictive performance, possibly due to the inclusion of both relevant and irrelevant conceptual information. A direction of future work in this case is to investigate multitask learning by grouping relevant concepts and modeling these concepts separately. Finally, I'll conclude by presenting a summary of our work and future directions. In this work, we demonstrate the potential and effectiveness of a hybrid stealth assessment framework for modeling student competencies through the use of a variety of models. We show the application of this ECD-based framework within a digital game for learning, and finally demonstrate that our approach induces higher performance in comparison to single model baselines. Some areas of future work include more complex feature engineering, alternate modeling techniques such as hierarchical modeling, and clustering alongside supervised learning. Multitask learning becomes increasingly difficult as the number of tasks increases, and training deep sequential models for 16 tasks using only 316 data samples is likely a limiting factor in the multitask model's performances, So evaluating multitask models on larger datasets would provide further insight into the performance aspects of this framework. Therefore, we also want to evaluate our hybrid framework using larger and more diverse datasets and student populations. Thank you for your attention.